Hello again, and we are now in Chapter 9. Chapter 9 is about optimizing a multi-layer perceptron, which is a kind of a neural network. And we use it as a classifier, and we want to optimize the parameters and the architecture of this classifier. So let's take a quick look at it. The multi-layer perceptron looks like this. It has input and output layers, which are defined by how many features we feed into the model and how many different, if it's a classifier, how many categories or classes we have. But in the middle you have hidden layers that can be of any size and number. In this picture you have two hidden layers. The first of them is the size of 6, the second is the size of 4. But like I said, it could be any, and still it will do the same job, but maybe will do a better job or lesser job, and it's sort of an art to find the correct architecture of this network, which is also similar to all kind of other neural networks. They have different architectures or different ways to configure the architecture, and we always have this challenge of finding the optimal way of setting the architecture. So we use here the MLP classifier from the scikit-learn, and if you look at it, by default it has one hidden layer of 100 nodes, but you define how many hidden layers and what are the sizes by setting that argument. And the rest of the argument are what we normally see as hyperparameters. So in our first attempt, we are going to just try to figure out the architecture, just try to figure out what are the best hidden layers that we can choose for the model to solve a particular problem, which is the classic iris classification problem. We have 4 inputs, 3 outputs. It's 3 categories of iris that we need to decide, and there is a data set, well-known data set, that we can use to train the perceptron, the multi-layer perceptron, and measure the accuracy or whatever other measure we want to optimize. So in this case, if we look here, there would be 4 nodes here, 3 nodes out here, and in the middle, whatever we want. So our program will try, the first program here, we'll go with anywhere between 1 to 4 layers, and each layer here we just set up some number. So the first layer will have anywhere between 5 and 15. The rest of the layers can have up to 10 nodes, but they can also have a negative number. If any of those have a negative number, we decided this layer does not exist, and also the layers farther are not going to exist. So if we have a negative number here, that means that there will be only 2 layers. If the negative number will be in here, then there will be really only 1 hidden layer. So this is how we use these boundaries to decide what is the architecture of the network. And we can try to run this to find out what is the optimal architecture within those boundaries that we set here. So I'm going to run this. It might take a while because we are trying different combinations. Each generation has several different individuals to try out. So by definition, this could be a lengthy process, but we have a sort of a smaller problem here. So it won't take that long, and we will wait for the results. So as we can see here, we ran it for 10 generations, and the best results we could find are 3 hidden layers with the number of nodes being 15, 5, and 8. And the accuracy we found was about 87%, which is reasonable for this kind of problem. The next program, we take it a little bit farther, and what we say here is, well, these hidden layers we can, or architecture that we called, we can set those, but we can also set all kind of other parameters. So these are hyperparameters that we have seen before that can be also set by the genetic algorithm. So we can now think of the hidden layer sizes as just one hyperparameter, one of several others, and let's try to tweak all these together, or several of those together. So the hidden layer sizes plus some of the other parameters. and maybe we'll get better results than the 87% that we see here. So in this program, as you can see, we have the layers. The first four are actually the sizes of the layers, just as before, but the next four parameters are actually standing for what activation function to choose, what kind of solver, what is the value of alpha, and what is the learning rate. All of them have certain boundaries or certain options that we can choose. So we're mixing the search for those and the layers, the architecture at the same, basically at the same search space that we are going to search on, and we are going to run this genetic algorithm on the same problem. And this might take a little longer because we have more parameters, more options. And let's run it and see. So as we can see here, the results are better than before. We now have accuracy of 94.7%, which is considerably better. And we have different sizes, somewhat different sizes for the hidden layers in combination with other hyperparameters that were found. So this combination basically decided both the architecture and some of the hyperparameters, and produced a pretty good classification performance. That is it for chapter 9, and we will continue next with chapter 10.